Okay, in part 2, what we're going to talk about is this idea of having an inverse relation. Okay. And we're going to talk about a few things regarding inverses. Okay. And first of all, the definition here, if we have an ordered pair AB, is in a relation if and only if the pair BA is in the inverse relation. Okay, that's ultimately the definition. But what happens here when we're dealing with inverses is the following. Okay, if I have a function that has an inverse, okay, then if I take something like y equals x squared, for instance, we use inverses quite often in equation solving. If I had y equals x squared, okay, the inverse of that turns out to be y equals radical x. Okay, because what inverses do to each other is the following. If I were to put something in for x, like let's say 2, okay, I would get out a 4. True? And then in the inverse function, if I put in the y coordinate, okay, then I would get back to the original x coordinate. So what inverses do to each other essentially is that they undo each other. Okay, whatever I put into this one, I'm going to get something out. And if I take the output and I put it into the inverse, I'm going to get back to the original input. Okay, and so therefore in this relation, what we're saying that is if the relation contains the point AB, then the inverse contains the point BA. So again, these two are inverses because this one contains 2, 4, and this one contains 4, 2. Okay, and we could do that with any point, no matter what we plugged in here for x. And there's a little bit of a stipulation on this one, which we'll get to in a minute. But whatever I plug in here for x, if I put in a 5, I'm going to get 5, 25. And if I put a 25 into this, I'm going to get back to what? 5. So anything that this contains, AB, this one is going to contain BA. It's going to retain the reverse point. Now, I'm going to start out by looking at this process with the same idea of having parametric equations. Okay, we already looked at the graph of this. Okay, and what's nice about parametric equations is that the inverse relation, okay, this is a relation, it's a line, right? Okay, the inverse of this is just going to be the flip-flopped x and y's. Okay, we're going to write 3t plus 4 for x, and 2t minus, oops, there's the wrong signs in here, so 2t plus 1. Okay, so we're just going to flip-flop the x and y, and that's going to produce the inverse of this parametric relationship. Okay, now I want you to see what that looks like in the graph. Okay. If we graph it, notice that it's another line. Okay, and there's something special about these two lines that I have here. Okay, and I'm going to show you with something special by graphing another line. Okay. And this line that I drew here, even though it was in disguise, is the line y equals x. Okay, and what do you notice about these two lines relative to that line y equals x? Okay. Okay. It's a reflection, isn't it? Okay. And that's going to be a geometric fact with any two inverses. If the two functions are inverses of each other, okay, they are going to be reflections of one another over the line y equals x. Okay, so that's a geometry property of functions that are inverses. And that happens anytime that one contains AB and the other one contains BA. Fair enough? Now, let's go back to our function mode and look at another graph. Okay, I mentioned this x squared equation, okay, and I had radical x as my other one. My claim was that these are inverses of each other. Okay, I'm also going to graph the line y equals x because I want to show that geometric relationship here when I look at these two graphs. Okay, so if I hit graph at this point, let's see what happens. There's my parabola, there's my square root curve, and there's my line y equals x. Now, two things that I want you to consider here. Number one is that if you look at this parabola, it looks like this branch right here and this branch right here are definitely reflections over that line. So that seems to make sense. But what about this branch over here? Okay, there's nothing down here. Shouldn't there be something down here if these are really inverses of each other? Okay, the answer is yes to that. But what the problem is that when we have a function like y equals x squared, okay, that doesn't pass the horizontal line test, similar to the vertical line test, if this does not pass the horizontal line test, okay, then its inverse is not a function. Okay, because technically if we talked about this branch over here, we should have something down here too. But then if I did that down here, wouldn't this not be a function? Okay. And so what happens is when we have a function like that that doesn't pass the horizontal line test, okay, we generally restrict the domain, which means we only look at part of it. So in the case of a parabola, if we started at 0, 0, okay, then wouldn't this branch right here, wouldn't just that branch only pass the horizontal line test? Okay, and therefore its inverse would be a function. Okay, so generally when we think of a function that has this situation where it's not, okay, what we call one-to-one, we'll look at that vocab in a minute, but if it's not one-to-one, in other words, doesn't pass the horizontal line test, okay, then ultimately, okay, we have to restrict the domain in order to actually talk about an inverse. Okay. Now, could we look at an inverse of the other branch if we wanted to? If we looked at the left-hand branch? Sure. Okay, and I'll graph it, and you can see it. It's just going to be the opposite of the square root of x. Okay. So if we put that in there and hit graph, okay, notice what it graphed. If I just look at this branch and this branch, and again, here's my line y equals x, do these or do these not look like reflections over that line? Okay, and they should, because they are. Okay. And now if you look at the function as a whole, and you look at its inverse, okay, now it looks like the whole thing is a reflection over that line. Okay, but the problem is that this inverse right here is not a function anymore. This is now doesn't pass the vertical line test. So bottom line is, if this doesn't pass the horizontal line test, then the inverse is not going to pass the vertical line test, is it? Okay. All right. Question so far? Ask you a question. Good. All right, let's take a look at a couple more ideas involving inverses. Okay. This is one of your definitions from your book. It says, if f is 1-to-1, and remember that 1-to-1 means passes the horizontal line test. Okay. So if f is a 1-to-1 function, which means it passes the horizontal line test, it's got some domain and some range. Okay, then the inverse function, which is denoted by, and it looks like a power here, okay, but we don't read this as f to the -1. We read this as f inverse. Okay, so when we see that notation, we read that as f inverse. So, okay, so again, and here's the key, that this is a function whose domain is R and whose range is D. In other words, they flip-flop domains and ranges. Okay, so if one has a domain of 0 to 5, then the inverse is going to have a range of 0 to 5. Okay, so they flip-flop domains and ranges. Okay. All right, and then the other fact here was that A-B business. Okay, if we put in A and we get out B from the function, then in the inverse, if we put in B, we get back to A. Okay, so that's just another illustration of that A-B that we talked about a minute ago. Okay. All right, now, with that said, one of the skills that we have to be able to do is we have to be able to find the inverse of a function. Okay, if I were to graph this 2x over x minus 1, I'm going to keep my y equals x in there so we can see the symmetry when we do this. So 2x and divided by x minus 1. You can see that we do have an asymptote there, as we should have expected with the x minus 1 on the bottom. So there's our line y equals x, and we want to find what is the inverse of this equation. Now, looking at that and trying to think about it as a reflection and actually coming up with an equation for what might be the inverse is virtually impossible. Okay? So luckily for us, there's an algebra technique that we're going to use to be able to figure out what the inverse is. Okay, and that technique is going to be illustrated by the following. This is right in your book. I'm just going to show this to you, and then we're going to actually do it. Okay, this is one of the boxes in your book here. It says, to find the formula for the function f, okay, proceed as follows to find the formula for f inverse. All right, so first of all, it says determine that there is a inverse by checking that if f is 1-to-1. Okay, so let's do that. If you look at this, is this 1-to-1? Okay, with this curve, remember disregard the line y equals x that I have here, but would that pass the horizontal line test? Sure. Okay, so it is 1-to-1. Okay, state any restrictions on the domain. This is where if I had y equals x squared, I would say, wait, that's not 1-to-1, so I'm only going to use x greater than 0 or x less than 0. Okay, I'm going to have to restrict it to something that is 1-to-1. Okay? Okay, and this is the key to the algebra part here. We're going to switch x and y in the formula. So whatever the formula that we're given, we're going to switch the x and the y. Okay, and then we're going to solve for y to get a new formula, which is going to be the inverse formula. And then state any restrictions on the domain of that if we need to. Okay. All right, so let's see that in action. So ultimately, if I'm given this function, I'm going to rewrite that as y equals 2x over x minus 1. Okay. And then if I do step 2 is to switch the x and the y. And this is what we mean by that. We're going to replace all the y's with x's, and we're going to replace all the x's with y's. Okay. All right. Now, step 3 is the part that is the most difficult because we have to do some algebra. Somehow here we have to get y by itself. Okay. In some cases, it might be very easy to do. Like, for instance, if I take the line y equals 2x plus 1, and I ask you to find the inverse of that, we would switch the x and the y. Okay. And then we would solve for y. So we would subtract 1, and then we divide by 2. So we'd ultimately get 1/2 x minus 1/2 equals y. And remember, in this case, when I label that, that's going to be labeled as f inverse of x. Okay, keeping in mind that this was our f of x at the beginning. Okay, so in some cases, it's pretty easy to solve for y and get the inverse equation. And remember, if I were to graph this and graph this, I would see that they are, in fact, reflections over the line y equals x. If they weren't, then something's not right. Okay, so that's a good check. All right, so algebra-wise, what are we going to do here to get y by itself? Okay, the techniques we have, if we have a y on top and a y on the bottom, what we need to do is get this y off the bottom by multiplying. So we'd go x times y minus 1 equals 2y. Okay. So that's going to be step 1. Step 2 is we're going to distribute. So we'd have xy minus x equals 2y. Okay. Step 3 is going to be get everything that has a y on the same side and everything that doesn't on the other side. So I'd subtract 2y, and I'd add x. So if I did that, I'd have xy minus 2y equals x. So again, I'm going to collect the stuff that has y on one side, the stuff that doesn't have a y on the other side. Next step would be factor out the y, because these both have a y in common. And then the final step is to get y by itself by dividing. So y times x minus 2 can be gotten alone by dividing by x minus 2. Okay. All right. Questions on the algebra steps here? Okay. Take some practice. Once you do a couple of these, and the algebra steps don't change really when you have that situation. But let's double check it here by graphing and see if we think that's right. So if we do our x divided by x minus 2, and we hit graph, and we look at the two branches individually, how does that look in terms of reflections? Seems pretty reasonable, doesn't it? Okay. All right. Questions so far? Anybody? Okay. All right. Okay, I want to look at just real quick. If we were to be given a graph like this, okay, is there a way we can graphically find the inverse of this? Okay. Well, one thing that we can see here is that we can plot a few points. We can see that this one has those 3 points at least. Okay. And remember, if I make an XY chart for the graph that I'm given, if I got -1, 0, and I have 0, 1, and I have 1, 2, and this is my f, then what would my f inverse have then? It would have 0, -1, it would have 1, 0, and it would have 2, 1. It would have to have all those reverse points, wouldn't it? So if I do 0, -1, that's here. If I do 1, 0, that's here. And if I do 2, 1, that's here. Okay, I would have those 3 points. Okay, I also could estimate some other points along here and some other points along here and plot a few more points. Okay, bottom line is, again, keep in mind that it has to be a reflection over the line y equals x. Okay, and so ultimately, if I were to plot a few more points, I could get the graph to look something like that then, couldn't I? I guess not perfect because I'm not a very good artist, but with that said, okay, key issue is that they need to be reflections of each other over the line y equals x. Okay, so if you plot enough points, you should be able to draw a picture of what that would look like. Okay. Questions on any part of the geometry part? Okay. All right, and then one final step here that we want to look at is this. This is a rule for proving that functions are inverses of each other. Okay. And what it boils down to is we're going to compose the two functions and show that that result is x. Okay.